so we are done talking about unit conversion and stuff, and we're going to get into now kind of actual physics. We're going to start with particle kinematics in one dimension. And so I want to take a second and describe what all these words mean, what all this means together. So particle kinematics in 1D. Is that hard to see in the back there? Okay. Yeah, I think, can I zoom in? I think I might just have to write bigger. Yeah. Okay. So particle. I think people tend to think of a particle as something very small, and particle physics does deal with very small things. But in order to understand the stuff we're going to do for the next several weeks, you need to understand that really anything can be treated like a particle. A particle is just a mathematical treatment. So I'm just going to write it as a treatment of an object and so we're treating this object as if it has, as having no lengths, but it does have mass. And because it doesn't have any lengths, it just exists at a single point. So it exists as a single point at the object's center of mass. Just sort of the middle of the object. Okay, so that's what it means that we're talking about a particle. We're not going to be worried about forces being applied and stuff at different points on a body and how that makes a body spin or anything like that. We're just going to be tracking the center of mass of the object as it moves around. And you can do this for tiny objects, but you can also use this approach for big things like planets and cars and whatever. Second, kinematics. So in kinematics, we're describing the motion of objects without concern for the causes. We're not thinking about the causes of the motion. And so in kinematics, the variables that we're going to be concerned with mostly are position, velocity, acceleration, and time. Okay, we're not going to have any forces, masses. Those are the things that cause motions, and we'll talk about those later. This is kind of an annoying thing, but the two types of, these two branches of physics have very similar names. So kinematics is as opposed to kinetics. I didn't make these. And so kinematics, the slightly longer word, is the one that deals with less stuff. Kinetics, the slightly shorter word, is the one that deals with more stuff. Okay, it has all of the kinematics in it, but it also includes forces, masses, energy. And then the last thing is 1D. What does it mean that we're working in 1D? 1D really means, in the most general way to describe it, it means at any point, an object only has two choices of where it can go. You know, it can go this way or it can go this way. For us, we're just going to think of it as motion along a line, and motion along a line is one dimension. So that's what I'm going to write, just motion along a line. But notice that you can also, like if you have a wire that curves through space and you have a bead that slides along the wire, that bead isn't moving along a line, right? It's moving along this curved path. But at every point, it can only go one way or the other way. So that's also one-dimensional motion, even though it's not a line. But the stuff we're going to talk about is along a line. So the measurable quantities that we're going to discuss are position, and I'll abbreviate that as a lowercase p. And in the same category as position, I'm going to mention displacement. We'll hear that a little bit, but it's really just, you're just really subtracting two positions to get a displacement. Velocity. Lowercase v. Acceleration. That's a lowercase a. And then the last one that relates to all of these is time. We're going to see how all of these change over time. And I'll abbreviate that with a lowercase t. And as we talk about these things, keep in mind the distinction between stuff that happens in the real world So a lot of times I'm going to mention, we're going to imagine putting stickers or something on the path of the object. That's in the real world. Like you could actually physically imagine going over and putting a sticker on a table or a street or something, okay? And the other thing we're going to see is, I'm going to call it math world, where we're talking about graphs and just mathematical ways of describing things. And it's going to be important to keep in mind which of these two you're thinking about at any instant, or it's pretty easy to get confused. Okay. So I'm going to here on real world, I'm going to say, okay, I'm going to talk about this in terms of like stickers that you actually can imagine applying to things. And in the mathematical world, we're going to be dealing with graphs mostly. Okay, so the first thing I want to get into is the definitions of position. So let's say there's a linear train track with a train moving along it. I can only draw old-timey trains. So this, whether we're here doing physics or not, this train at this instant has a location. It is somewhere, you know, there's no denying that. What do we have to do in order to take this location and turn it into a numeric position? Okay, so the positions we're going to talk about are just going to be numbers, so we can do calculations with them. We're treating this train like it's a particle, which means it only exists at a single point. So that single point is at its center of mass. So this is the symbol for center of mass. Okay. So what do we have to do to express this location as a numeric position? Well, we have to do two things. So the first one is we have to choose the location of a zero position in the real world. Okay, so you can imagine placing a sticker at this point that you're going to just arbitrarily call zero. And the second thing that you have to do is you have to choose. Now, remember, we're moving along a line, so there's only two directions we care about. And we have to decide which of those two directions we're going to call positive and which one we're going to call negative. Okay. So we have to choose a positive and negative direction. You could think of it as just choosing the positive or just choosing the negative. Then the other one would just be the opposite direction. Okay, so once you make those two choices, like let's say, here's the sticker that I'm going to put down that says there's the zero. Okay. And now I have to choose the positive and negative direction. Let's say I'll choose this to be the positive and this to be the negative direction. And now we can measure from the zero position to where the train is. So let's say this is 1 meter, 2, 3, 4, 5. So this train is 4.5 meters in the negative direction from zero. Okay. And that means that the position is negative 4.5 meters. Okay, so what the position of an object is depends on two things. What you're choosing as your reference position, that 0, and which direction you're calling positive and negative. And really, this is just a mathematical version of the way you always would describe to someone where an object is located. If someone says, "Where's Super America?" you give them a reference position. You know, you say, "Oh, do you know so start at Normandale or whatever, and then go 1 mile west." Okay, and with those two, giving them by giving them a reference point and then a distance and a direction, you can get them to the location, and that's what we're doing here. The units for position are always units of length. And so the SI units are meters. And so most of our calculations we're going to do in terms of meters. Sometimes questions will ask you about a displacement of an object from one instant to another instant. And the displacement is just the later position minus the earlier position. So for example, if the train if the train's position is negative 4.5 meters at one instant, and then it's positive 2.0 meters at a later instant, then the displacement over that time interval is, so which one are we gonna, so we're gonna subtract these two one way or the other. Which one do I want to write first in the subtraction statement? 2.0, right. We want the later one. So we have 2.0 meters. And then we're going to subtract the earlier one. So that's minus negative 4.5 meters. And if you subtract those, you get positive 6.5 meters. So over that time interval, the object moves 6.5 meters in the positive direction. Okay, so now we want to think about how the position relates to time. So to relate the position to time, we're going to imagine a stopwatch going as this motion happens. So you have this stopwatch with a start and stop button and a reset button, you know. And so we have to choose one more thing in order to relate the position to time. We have to choose an instant to call zero time. And you can think of that as the instant that you turn the stopwatch on. So you click it on at 0, and now the stopwatch is counting up as the motion happens. Okay, we don't have to think about a positive or negative direction for time because everything's going to happen forward in time. And one thing I just want to say is that for a lot of the things we do, we're also going to have to choose an instant to turn the stopwatch off. Right now, that's not going to come into it, but we're also usually going to choose a single instant to stop the stopwatch. Okay, so let's put these things together in a position versus time graph. So this is a P versus T graph. And it says at time equals 0, the position of the object is negative 15 meters. At time equals 1 second, the position is negative 10 meters. At time equals 2 seconds, the position is negative 5 meters. And at time equals 3 seconds, the position is positive 1 meter. And we want to draw a position versus time graph. Okay, well, these graphs are always going to have position on the vertical axis and time on the horizontal axis. Remember, in math, when you talked about functions, you always put the independent variable on the horizontal axis and the dependent variable. Like, for example, you would put x on the x-axis and then your function value f or y on the y-axis. And that's what's going on here. The position of an object is a function of time. You can't ever have two different positions of the same object at the same time, okay? So the times that we care about are time equals 0, 1, 2, 3. That's all I gave. And the positions are, so this is 5, 10, 15 in the negative direction. Up above would be the positive direction. And so at time equals 0, the position is negative 15, so that's this. At time 1 second, the position is negative 10 meters, so this. At time 2 seconds, the position is negative 5 meters, so this. And then at time 3 seconds, the object is at positive 1 meter, so this. And the graph would look something like this. Anybody have any questions about that? Okay, so the first kind of problem that you're going to have to do a few of is like this one. So I'm going to describe like a physical motion, and then we're going to make a position versus time graph. So let's say we have a setup like this. There's a shed here. There's a fire hydrant. And then there's a car. Okay. And the distance between the shed and the fire hydrant is 15 meters. And the distance between the fire hydrant and the car is 10 meters. And let's say that a person walks from the shed to the car in 15 seconds. Then the person walks back to the fire hydrant. In 10 seconds. And we want to draw a position versus time graph. And we're going to do it for two different cases. First, we're going to assume that we put down our position equals 0 sticker at the hydrant. And the positive direction is to the right. And we're going to turn on the stopwatch, so our time equals 0 is going to be at the start of the motion. Then after we're done with that, we're going to draw a position versus time graph of this same motion, but we're going to make different choices of our position equals 0, positive direction, time equals 0 instant. So this time, position equals 0 is going to be at the car. The positive direction is to the left. and time equals 0 is 5 seconds before the motion starts. Okay, so drawing out kind of a diagram of what's happening is helpful in problems like this. So I'm gonna first in black write out the stuff that happens, and it doesn't have anything to do with our choices. Like, we're just hiding in the bushes watching this guy. We don't decide whether he goes, we don't make him turn around when he gets to the fire hydrant. We just let him do his thing. So we're just watching as he goes from the shed to the car back to the hydrant. And we have no control over that. So here's the path that this person follows. Here's the shed. Here's the hydrant. Here's the car. And the person starts here. So now I'm going to draw the motion that we also don't have any control over. The person goes from here, past the hydrant, gets to the car, turns around, and goes back here. Okay? And then there's some other things that we don't control. The distance between the shed and the fire hydrant is 15 meters, right? Mm-hmm. And between the fire hydrant and the car is 10 meters. And the elapsed time in going from the shed to the car is a total of, that was also 15 seconds, I think. Okay, and then the elapsed time in going from the car to the fire hydrant is 10 seconds. So all this stuff in black is stuff that we don't control, okay? But now in red, I'm going to go through and choose the 0 position, the positive direction, the 0 time. And okay, so let me do time first. So for part A, it says time equals 0 is at the start of the motion. So right when the person starts walking, the time is 0. If you start at time 0 and then 15 seconds goes by, what does the stopwatch say here at the car at this second instant? You can just think of it as adding time. So it's just 0 plus 15. So the stopwatch here would say 15 seconds. And now if another 10 seconds goes by before the person gets to the fire hydrant, what does it say when the person gets to the fire hydrant? 25, yep. So those are the times. And now we're going to think about the positions. Yes?
But didn't you say that T is at 5 seconds before movement?
That's for part B. We're going to spend a little while doing this whole part A first.
Oh, okay.
And then we'll go through it again, part B, in case you're not sick enough of this scenario. Okay, so now we have to think, where are we putting the 0 position sticker? We're putting it at the, so it's important to notice that that sticker doesn't have to go where the object is, okay? So we're putting that position equals 0 sticker on the fire hydrant. Okay, so I'm gonna mark the fire hydrant, and whenever the person gets there, they're at 0 position.
Why?
Just because that's what it said here. I'm just trying to show you that you can do these problems with different choices of 0 position, positive direction, and the things will look, your solutions will look different. And so these choices are sort of fundamental to the answers you're going to get. So all it is, okay, so like going back to the Super America example, so I could say start at Normandale and go west 4 miles. Or I could say start at Bloomington Kennedy and go east a 1/4 mile. And neither of those are wrong. We just chose a different thing to reference to. Okay, so this 0 position sticker is just a reference, and it's arbitrary what you choose as your reference. And so for part A, it just says, we're putting this sticker down on the fire hydrant and measuring everything compared to the fire hydrant. Okay, so the fire hydrant is our 0. And our positive direction is to the right, which means our negative direction is to the left. So this is positive. This is negative. And now we can label these other 2 points. If you start at 0 and go 15 meters in the negative direction, what number do you arrive at? Negative 15, perfect. And if you start at 0 and go 10 meters in the positive direction, what number do you arrive at? Positive 10, yep. Okay, so here's what we know now. We know that, so if you look at the black hook-shaped thing that represents the motion, we know that the person starts at time 0 and at position negative 15. Then the person at time 15 seconds is at position positive 10. And then at time 25 seconds is at position 0. So I'm going to write out a little table just for bookkeeping purposes where I mention the time and the position. The first time is 0 seconds, and the corresponding position is negative 15. The second time that we know is at 15 seconds, and the corresponding position is positive 10 meters. And the third time is 25 seconds, and the position is 0 meters. And now all we're doing is plotting those points on a position versus time graph. Position always goes on the vertical axis. Time always goes on the horizontal. The times we care about are, so we got 5, 10, 15, 20, 25 seconds. And the positions we care about are negative 15 meters and positive 10 meters. And it starts at 0, negative 15, plot the point 0, negative 15. Then plot the point 15, positive 10. Then plot the point 25, 0. And it looks something like this. You don't have to worry. It would have a curve to it, but you don't have to worry about the curve. Just connect the points. Any questions about that? You want to take a few minutes and try to work your way through part B, sort of following those steps. And I'll go through it at the end if you're still not following what's going on, but try to do it. Talk to the people next to you if you need help, or talk to me if you need help. And yeah. Yep. Oh yeah, thank you. Let's see. Can you see that? Is that, okay. Okay, so for part B, now the stuff that we don't have any effect on looks exactly like it did before. So all of this stuff in black, if I would have thought of copying this, I could just paste it because none of that'll change, okay? The only stuff that's gonna change is what we call our zeros, what that makes the other positions, stuff like that, the stuff that's in red in that. So I'm gonna just draw this again. We know the distance between these is 15 meters. The distance between these is 10 meters. And we know the motion goes from here to there to there. And we know this part takes 15 seconds and this part takes 10 seconds. Okay, so now our position equals 0. We're going to put that sticker down at the car. So this is going to be our 0 position. Our positive direction, we're going to choose that going to the left. So this time from 0, we have our positive going this way and our negative going this way. Okay, so if you start at 0 and go 10 meters in the positive direction, what's the value here? Positive 10, yep. And if you start at positive 10 and go another 15 meters in the positive direction, what do you get to here? Positive 25, yep. And now let's think about the times. So it says that this time the stopwatch is turned on 5 seconds before the motion starts, okay? So when the motion starts, the stopwatch already says something on it. It doesn't say 0 anymore. What does the stopwatch say at that instant? Yep, 5. Perfect. So now we're at 5 seconds when the motion starts, and 15 more seconds go by. What does the stopwatch say at this point? 20 seconds, yep. And then 10 more seconds go by. What does it say at this instant? 30. Perfect. And now we can just read these values off and put them into this table like I did last time. I'll put time over here, position over here. The first instant where we know these two things is at 5 seconds. And what's the position? Positive 25, perfect. The second instant is here. What does the stopwatch say? 20. And what's the corresponding position? 0, yep, perfect. And then the last one, the stopwatch says what? 30. And what's the position? Positive 10, perfect. And now it's just a matter, again, of plotting out those points. So the position is on the vertical, time is on the horizontal. We have 5, 10, 15, 20, 25, 30. And the positions we care about are 0, 10, and 25. And so we'll plot 5 seconds, 25 meters. We don't know what happens before that. Maybe it just stays there, but I'm just going to leave it blank. The second point is at 20 seconds, 0 meters. And the third point is at 30 seconds, 10 meters. And so connect those points and the graph looks something like this. Do those graphs look the same? I mean, there's definitely differences. There's some similarities too. You can see that the shape is similar. What happened was, just by the way, in case you're interested in the shifting and flipping and stuff that's going on here, changing what we called our 0 time shifted it horizontally, okay? Changing what we called our 0 position shifted it vertically, and changing what we called our positive and negative direction flipped it. Anybody have any questions about that? For the assignment that I'm going to give you today, you'll have a couple of problems like this to do. But it's just getting used to the relationship between the things that you have to choose to do a problem and the physical things happening in the real world. Let's do one more. Okay, so let's say a ball rolls along the floor from a distance of half a meter from the wall. And let's say it takes 1 second for the ball to hit the wall. and then it takes 1.5 seconds for it to bounce back to the starting point. So choose the 0 position at the wall, the positive direction to the right, and time equals 0 at the start of the motion. And draw a position versus time graph. Okay, so take a few minutes and see if you can work through. So, again, I mean, I think you don't have to do this part, but I think it is helpful to draw out the motion, and I have 2 colors up here, so for me, I just do it in the 2 different colors. But we have the 2 points that matter, where the ball starts and stops, and then the wall that it gets to in the middle. And we know that the distance between these is 1/2 meter. And we know that the object starts here, rolls here, hits the wall, and comes back to here. And we know the first half of this trip takes 1 second, and the second half takes 1.5 seconds. So we haven't yet put anything in about our 0 position and stuff. Now, position equals 0, it says, is at the wall, so this is 0. The positive direction is to the right, so positive is this way, and that means negative is this way. And if you start at 0 and go 0.5 meters in the negative direction, what's the position here? Yep, negative 0.5 meters, perfect. And then for times, the stopwatch begins running at the start of the motion, so this is at 0 seconds. 1 second later, it's at 1 second. 1.5 seconds after that, it's at 2.5 seconds. And now I'll write out the table. The first point we know everything about is at 0 seconds, and the position is negative 0.5 meters. The next instant we know is at 1 second, and the position is 0 meters. And then the last one is at 2.5 seconds, and the position is back at negative 0.5. Okay? And then it's just a matter of graphing it. So we have 0, 1, 2, 2.5. And the positions that matter that show up are 0 and negative 0.5 meters. And now just plot it. 0, negative 0.5, 1, 0, 2.5, negative 0.5. Any questions about that? Okay. The next stuff we're going to get into is defining velocity and acceleration. And the meaning of velocity is it measures how quickly the position is changing. And let me actually say it measures how quickly and in what direction the position is changing. One thing that you want to remember is that you can break up the velocity into two pieces, a direction piece and a absolute value piece or a magnitude. So remember this. You can break up the velocity into a sign. That's the direction. And an absolute value. And I'm going to call that absolute value the magnitude. And here are the meanings of those two things. First, the magnitude of the velocity is the speed. So a velocity can be positive or negative, but if you just chop off the sign and treat the absolute value, that always tells you the speed at that instant, like the speedometer speed. And the second thing is the sign is the direction the object is moving at that instant. Okay, so for example, if the velocity of an object is negative 35 meters per second, what are the speed and the direction of the object? Speed and the direction of motion. The speed is just the absolute value, so that's equal to 35 meters per second. And it's moving in the negative direction. Okay. So like if your speedometer on your car measured velocity instead of speed, and you took a trip, let's say you took a trip straight to the Iowa border, so you just go straight south for how far would that be? 100 miles or a little more, and then go back straight the same way. As you were going, well, depending on what we called positive and negative, let's say we call our positive direction north, okay? Then as you were going south toward the Iowa border, your speedometer would say negative 60 miles per hour. And then when you turned around and headed back towards the Twin Cities, you'd be moving in the positive direction and your speedometer would say positive 60. Okay. The units for velocity are always units of length divided by units of time. And so the SI units are meters per second. So that's what we'll use most for velocity. Yes?
In this case, do we still only have two options of going either one way or the other?
Yep. Yes, we're still only doing 1D kinematics, and we'll be doing that for at least a week.
Okay.
Yeah, maybe 2 weeks, up to 2 weeks. On a position versus time graph, the velocity at a given instant is the slope of the tangent line. Okay, so for example, if this is a position versus time graph, position is this way, time is this way. Let's say this is the instant A and this is the instant B. A tangent at the point A is like this. Does that have a positive or a negative slope? Negative. And at the instant B, a tangent is like that. Does that have a positive or negative slope? That has a positive. So at instant A, it says that the object is moving in the negative direction. And at instant B, the object is moving in the positive direction. Okay, so let's try something where we put these all together. So let's say we have an object that's moving along a line like this, okay? And we'll call positive down this ramp, and negative is up this ramp. And a position versus time graph of the motion looks like this. And let's identify this point here. And the question is, at the chosen instant on the position versus time graph, is the object moving up or down the ramp? Okay, well, we can figure out the sign of the velocity by figuring out the slope of the tangent. So a tangent line is like that. So is that a positive or a negative slope?
Positive.
Positive slope. And so we know that the velocity is positive, and the sign of the velocity tells you the direction it's going. So if the velocity is positive, it's moving in the positive direction, which is down the ramp. So the object at this instant would be going this way. Any questions about that? I think none of these pieces of understanding what velocity tells you are hard to understand on their own. The hard thing is sort of storing it all in your head. And so as you go through these problems, just keep reminding yourself like what the sign means, what the absolute value means, how it relates to what you see on a position versus time graph. You're just trying to store all that in the same spot of your brain, you know? Okay, I think that's a good place to stop. On Thursday, I'll talk about acceleration. And okay, look on D2L for an assignment.